So welcome again to the introductory workshop in this Eurofriend session. Today I will talk about the hydrological modeling framework HydPy. My name is Thomas Recknagel. I work as a hydrologist and in the field of hydroinformatics at Björnsen Consulting Engineers, a German company. My presentation has two parts. First, I want to talk about the HydPy. I'll bring you some overview and background. And then it will get more technical and I will guide you through the basics of HydPy, and hopefully it will help you to get started with HydPy. During the presentation, I will show you some examples, Python scripts or Jupyter notebooks actually. And you can launch these examples from MyBinder. So if you go to the website mybinder.org, you should enter this Git repository and then click launch. And if you're a little bit patient, sometimes you have to try several times, you will get this MyBinder view menu where you can go into the folder tutorial and you will find the Jupyter notebooks I will later talk about. So what is HydPy? HydPy is a free and open source hydrological modeling framework. You can download it from GitHub, but you can also install it directly with pip. So as you might got now, HydPy is written in Python. It's a community project. Everyone can contribute to its development. It follows modern standards of software development. And it is already in operational use for hydrological forecasts in Germany. The second link is the link to the HydPy documentation. Here you can see the river catchments where HydPy is already in operational use. So there is a big hydrological forecast for the whole Rhine basin, which is done by the German Federal Institute of Hydrology. The state of Saxony is operating a hydrological forecast system, which is in parts already in operational use based on HydPy. And there are also some smaller catchments with projects based on HydPy that are already in operational use. Here on the right side, you can see some graphical user interfaces, but these are not part of HydPy. So HydPy is a pure software framework. If you work with HydPy and nobody else does give you a graphical user interface, of course, that's possible. So that's, for example, what we do also for our customers. But the core of HydPy is pure Python. So if you work on this level with HydPy, you would need some Python knowledge. And how much depends on what you plan to do. If you just run some prepared HydPy projects, you need no or very little Python knowledge. Or if you want to change some parameters, that's also fine without big Python knowledge. But if you want to prepare your own application model or completely do new models in HydPy or even enhance the framework itself, then you might already need quite a lot of Python knowledge. Some words about the history of HydPy. HydPy originates in a research project at the Ruhr University in Bochum. And from the beginning, Christoph Tyralla is the main developer. And actually, he's also here today listening to how I speak about his baby. So if there are later any questions, I'm glad that Christoph is also here, who, of course, has a much deeper knowledge about his software project. Of course, also others over the time have contributed to HydPy already, but yeah, Christoph Tyralla is the main developer. First use cases with HydPy have been developed at the German Federal Institute of Hydrology. So the first HydPy release for operational use was in 2017. And since 2018, Björnsen Consulting Engineers is developing several projects based on HydPy, for example, hydrological forecasts for the German federal state of Saxony. The actual release is HydPy 6, published yesterday, with a lot of new features. Yeah, and I said until today, Christoph Tyralla is the main developer of HydPy. And yeah, the term reproducibility in computational hydrology especially is a subject we've heard already quite often here in the Eurofriend workshops and otherwise as well, of course. I think I did a session 2 years ago about how R can help you to improve reproducibility. And yeah, HydPy is definitely a great tool for improving reproducibility of hydrological workflows. So here are some points why. First, of course, it's on GitHub, so all ever published versions are and will stay available. If you need older versions, for example, to reproduce old code. From the beginning, HydPy had a great focus on standards of modern software development. So you see all these batches, we have a 100% coverage. That means that all code in HydPy has unit tests or doc tests, which run this code for tests and make sure that the code works as it's supposed to. We follow and fulfill the PEP 8 Python standard. And for example, all discussions on the development are also public on GitHub, so everyone can just open new issues if there's a bug, if there's a feature request or something like that. Another good point about HydPy is that, or as you know, Python is a scripting language, so normally numerical computations are significantly slower in scripting languages like Python or R compared to compiled languages like C or Java. And therefore, we use C for performance critical functions. However, thanks to the Python library Cython, these functions don't have to be written directly in C, but are transformed from Python code into C. So that was the first part, overview and background of HydPy. And yeah, now let's go into the hands-on session. And let's see how you can start from scratch if you want to work with HydPy. First of all, some words about nodes, elements, networks. Normally, you will use HydPy to create distributed hydrological models. So that means catchments are subdivided in units like hydrological response units or channels, and you have different models to model these processes. And yeah, here try to find a really old depiction of a catchment and its subunits. And of course, we have similar structures in HydPy. So if you do distributed hydrological modeling, you will end up with a network with different units. In HydPy, we call these units nodes and elements. And everything together is a network, of course. So in the HydPy world, elements or element instances are central components of each HydPy project's network. They usually represent places where something needs to be calculated. For example, the subbasin of a catchment where you want to calculate runoff generation or concentration, or river or channel flow if you want to calculate flood routing. Within a project, each element instance has a unique user-defined name. Elements cannot perform calculations by themselves, but they require application models. each element instance handles a single main model. And yeah, the element's task is mainly to connect its model to the network and enable data exchange with other models via nodes. So HydPy only provides a single element type defined by the class element, which can handle all different model types. Nodes, on the other hand, are the second essential components of all networks. They allow specifying which model instance passes which type of information in which direction. Nodes have different types, like variables. For example, if you have a runoff, you have a node with variable Q. Typical places for nodes will be basin outlets, river mouths, or stream flow gauges. And also within a project, each node instance also has a unique user-defined name that serves to identify it. So in general, you can say elements are only connected to nodes and nodes are only connected to elements. And yeah, the term network addresses the spatial connections necessary to model a catchment consisting of more than one subbasin, and it combines consistently coupled element and node instances. And after this little theory, we will now go to the first tutorial, and I will switch from this PowerPoint presentation to a hopefully prepared Jupyter Lab. Yeah. So I will just check if my binder session is still active, because normally there comes a timeout. I will just show you how, if you use my binder, you could now go to tutorial and open tutorial 1. Still seems to work, but yeah, I will continue on my local Jupyter notebook just so that I will not have any timeout using my binder. So now, if you are familiar with Jupyter notebooks, so we have cells with code lines, and between there are some comments. Unfortunately, I didn't manage to do all the comments between the lines, so I might later still update the tutorial with some more comments of what we do. So we start, if you want to create nodes and elements, we start easy. We import the node and element class from HydPy and create an instance of a node, instance of an element. Both get a name, and also the outlet of the element is the node we created one line before. So if you run this, and then I just write the name of the variable holding the element, you will get this output. So you can see, okay, I have an element with the name element1, and the outlet is a node with the name auto1. Later in the next tutorial file, I will explain a little bit more about this instance of the class HydPy I created at the very beginning. So actually, if you will work with a HydPy project, you will always have an instance of the class HydPy, which is your project. So I created this at the beginning, gave the name example1. And yeah, this instance of the class HydPy has a lot of attributes. For now, it's just important that it holds all the elements you have in your project. It holds all the nodes in your project. So I created a new element, and I just assign this element to the HydPy project, so that the HydPy project knows that E1 is part of its elements, and also that N1 node is part of its nodes. And yeah, now we can already, oops, okay, I should always start from the beginning, of course. So now we can, for example, check some attributes of the element. for example, element has a name, element 1, of course, we know because we called it element 1. Element has an outlet, so we can also access this attribute, and we will see, yes, the outlet is one node with the name outlet 1. So if you know Python, you know that with the command dir, you can check all the attributes of objects. So beside the private methods and attributes here, you will see there are a lot of more. Also already you see there are functions to plot something, there are functions, methods to save something. So quite a lot. You can check all the stuff in the reference guide, but yeah, for now we just have to know that the element has a lot of attributes. We can access it. And we can see here it has a model attribute, so we can also try to access the model attribute. And there's an error. And for people who don't program very often, error messages can sometimes cause panic attacks. However, error messages usually provide a good indication of what to do next. And if you read carefully, here's written the model object of element 1 has been requested, but not been prepared so far. And yes, I said the element itself does not calculate anything. An element needs a model, and so far we did not assign a model to the element. So this will be the next step. I will switch back to the PowerPoint presentation. Yeah. Models. HydPy has implemented already a lot of models, and also a lot of, for example, land models, which that model the processes of subbasins. So we have implemented a model called HydPy-H, which is made after the HBV model, HBV 96 model, you might be familiar with. There's another quite in Germany and German-speaking countries, quite popular hydrological modeling system, LASEM. We also have a HydPy-L that already has a lot of functionalities of the LASEM hydrological modeling system. And also the French model JR4J is implemented in HydPy. Our version is called HydPy-G. And also Dutch model for lowland hydrology, Walrus, is available in the HydPy world. It's HydPy-W. So what is one advantage of HydPy? You can combine models. So you can make a project. Here I have the squares denote elements. The triangles denote nodes. So this is a simple network with 1, 2, 3, 4, 5 elements and 3 nodes. And so these elements, I have 3 land models that model the processes and subbasins, and I have here 2 stream models that model the flood routing in the channel. And you see, we can, in one project, we can combine different models. So we can combine one subbasin, which gets simulated with the HBV 96 approach. We can have maybe a lowland subbasin modeled with the Walrus approach, and we can have another subbasin modeled with the HydPy-L approach. So the LASEM approach. So we are really free to combine all these in one project. And that's not all. With the new release, HydPy 6, which just was published yesterday, we have introduced a new concept of submodels. So for example, many land models, they need to calculate actual evapotranspiration. And in different models, also LASEM has different options, different approaches to calculate the actual evapotranspiration. So we thought it's a good idea to not for HydPy-H and HydPy-L program the functions that calculate evapotranspiration, but better reuse it. So you can couple submodels to such processes. So in this example I show here, I have two elements with a HydPy-H model. One uses a submodel with the Morsen approach for actual evapotranspiration, and another one uses the HBV96 approach for calculating actual evapotranspiration. And like, if that's not enough, there are even submodels. So if you want to calculate actual evapotranspiration, you might need the potential evapotranspiration. And again, you can couple the submodel with different submodels to calculate the potential evapotranspiration. So it's like a big game with building blocks you can combine together however you want. And yeah, that's I think quite an approach that is quite new for such hydrological modeling frameworks. So now we switch back to our tutorial, and we will learn how we assign a model to an element. So this is in the HydPy tutorial 1. This is step 2, assign a model to an element. So before we assign a model, we need to tell HydPy about the time frame. So we have this, later I will talk more about this pub object. It's a little bit magical because you import something, you import a module, but then you don't, like when we imported, I go back, when we imported the node or element class, then we created an instance of node and element. But here with this pub object, we don't create an instance, but we immediately use it. So that's a singleton. And yeah, that's at the beginning, that can be a little bit confusing, that you, especially if you are used to, work with classes and then first you create an instance, then you use it. So here by importing this class, you immediately have an instance you can use. And this is a singleton. That means you only have one pub instance for the public properties for your project. And one of the public properties is the time frame. So here we set a time frame, very easy manner, from 1st of January 2000 to 5th of January 2000, and we have a time step of 1 hour. If you work interactively in the Python shell, a convenient way to assign a model to an element is to do a wildcard import from the model module and to call the method parameter step directly after. So this call of this method also is a little bit magic. That's why it's important to know what's happening here. So after importing, after doing this wildcard import from our, in this case, HLand96 application model, we call parameter step 1 day. And by calling this method, there will be created some useful objects in the namespace. So for example, it will create an instance of the respective model class. So we call this, actually I should always forget to run everything. So run, and run. Yes. So now we have in the memory, there is obviously an object of the class HLand96. Again, the model objects have attributes, like we can check the name. And yeah, then again, we create an element, or actually it should still be created. And but the important thing is that here we assign the model. So this model, which was the instance of the model, which was created by importing everything from the module HLand96, then calling parameter step, and then we assign this model to the attribute model of our element. So now we have an element E1 in which the model HLand96 lives. And remember, each element can only hold one model. So we will repeat in a little bit different manner, but we will repeat these steps again in the next tutorial so that it really gets clear how we create a project. So don't be worried if it's a little bit fast now. We will do a similar thing again in a moment. I switch back to the slides. Yeah, next topic, parameters. So in hydrological modeling, parameters represent properties described by numbers that often depend on the spatial characteristics of a catchment, but are not changed by the model equations. That's how it's explained in our HydPy user manual. In HydPy, we differentiate 4 groups of parameters. Control parameters, which are the most important. They all the control parameters that directly control the models. Then some derived parameters, which the user will normally not set himself, but they will be derived from the control parameters by equations. Then there are fixed parameters and solver parameters. Solver parameters, normally it's about, for example, the differential equations which underlie the modeling, and they can control the accuracy of the solvers and stuff like this. The most important are the control parameters, and in the next step in the tutorial we will learn how to set the control parameters. And yeah, if you want to know, or if your question is, oh, how do I know which parameters are there? You can go to the HydPy documentation, and each application model you will find in the list of model families. So yeah, maybe a word to the term application model. So we have, here you can see we have different models, for example, HydPy H. These are all models that are based on the HPV96 approach. But again, there are different application models, because also in HPV96 there are different options, different ways to do things. And so all the possibilities, they are contained in the model HydPy H, and an application model is like choosing the right approach for different things, for example, for calculation of snow melting or stuff like this. So HLand96 is an application model, and an element is always connected to an application model, not to the model like HydPy H, but to an application model like HLand96 is. And if you go in the HydPy documentation, if you check out the documentation of such an application model, you will find the necessary control parameters explained. And yeah, of course, HPV96 is already quite a complex model. So if you want to set it up and set all the parameters, of course, it's necessary that you read a little bit about the HPV96 model. But yeah, everything is explained here in the documentation. So now, assigning parameters, we go back to the Jupyter Notebook tutorial 1. If now that we have assigned the application model to our element, we can access the attributes of the application model. So it has, for example, attribute parameters, and then parameters again has an attribute control. So this will list us all the control parameters, and we see none of the control parameters is set yet. So we can easily set these control parameters just by calling them, and as an argument set, if it's a numerical parameter, then the number is the argument. And so if I run this part, yeah, I run this and then I run this. And now you see, for example, the area of the subbasin and the number of zones and so on. These are already set. The others are still missing. So I will not talk about all these parameters now, of course, but I will just set the rest of the parameters. And now they are all set, but we still need to set the submodel, and that's what I explained some slides before, that you can combine different application models with different submodels. So this is how you choose a submodel. So in this case, we add to our model of element 1, which is the HLand96 model, we add a model for actual evapotranspiration. And again, the name of the model we give here as an argument, and the available models or application models, application submodels for actual evapotranspiration, you will find again in our documentation. So there you can see which choices you have. And you will also see which parameters the submodels need. And here we set these parameters for the submodel. And then I know it's a little bit complicated, this one. Again, for the submodel, we need a submodel for the potential evapotranspiration. And again, we choose a submodel. Also here we can find in the documentation the list of models for potential evapotranspiration. And we choose again the HPV96 approach. And we set the necessary parameters. And now if we run this, we should be all set. And yeah, with this command here, we will go through all parameters and also through the parameters of the submodels. And we see now everything is set. Then we need to call some more methods, which will just update parameters, will update the derived parameters I talked about, parameters that are dependent on our control parameters, but that we don't set directly. And then we call prepare all series, which will reserve the memory and stuff for all our input series and so on. And we also need to do this for our submodel and for the node as well. And and then what is still missing before we can do a simulation? So we have a model, we have parameters, we still need our driving forces, we still need our input data. So for a rainfall runoff model, it's probably precipitation and temperature, at least. So, and these time series we need are they're not called sequences. So sequences is a term we have in HydPy. So sequences are in the HydPy manual, we say it's properties that change during a simulation run. So these properties can be external forcings like precipitation or calculation results like discharge. So we have different groups of sequences: input sequences, state and log sequences, factor and flux sequences, inlet, outlet sequences. I will not go into detail now, but important is now that we have that if you need meteorological forcing, we need to set some input sequences. And later we will see how we read these sequences from time series. But for now, we will just set these sequences directly. So again, we have our element E1. It has our model, which is HLent 96. And the model has also an attribute sequences. And there we have inputs. And this holds the, maybe to make this a little bit easier, I will just call this. So now I just look at this object. So the input sequences of our model, and we see there are two input sequences, P and T, which stands for, in this case, for precipitation and temperature. And we see there's nothing set yet. If you call the sequence, it will always show you only the last value. So if you want to see or set the whole series, you have to access the attribute series of the sequence. So this would be calling the sequence P for precipitation, no value set. If you access the attribute series, you see all the values. We have, I think, 5 days and hourly steps. So all the length is already set, but we have no values yet. So that's why in the next step, I set an example series for precipitation. I will set an example series for temperature. And I will also set an example series for potential evapotranspiration. No, for normal evapotranspiration, for the submodel for the potential evapotranspiration. And now we can easily, if we have set it, we can use the method plot input series of our element. And you see now we have already all the input series set. So we have a model, we have a parameter set for the model. We have forcing data, meteorological forcing data. One thing is still missing, and that's the initial conditions, because no system starts without being in a state from the beginning. So we will set the initial conditions again in the documentation of the HLent model. You can check out which of these, for which states these abbreviations stand for. So it's SM as soil moisture, for example. So I will not dig into this now. I will just run it. And now we can check if it's set. Yes, it's all set. And now we can already simulate. And we can have a result. Yes, so we already have a result. And this is interesting. I can check in this case, the total outflow. I had one element with an outlet. The outlet is the node. So everything which comes from the element flows into the node. So I can get this series of discharge if I access the sim series of the node N1. But I can also access the same if I go to my element and check the flux sequences. Qt is the total discharge, and there I can access the same series. And of course, I can also plot it. And there we are. So I know it's a lot of steps, but with these basics, and it's the same way to set up a model all the time. So with these basics, you can easily now set up models for subbasins, and you can try this on either on my binder on your local machine. You can take this tutorial and maybe try to, instead of doing an H-length model, try to do an LASM-like model, an L-length model, and then you would have to check out in the documentation which are the right parameters you have to set. So you can try to check what happens if you simulate our example catchment with another model and compare this. Or you can do a lot of other nice things. Yes, so that was our first example. We are already, it's already nearly 5. Of course, I had to restart, so I hope you still have a little bit patience. I will go back to the, oh, why doesn't it? There we are. I will go now to the next tutorial, and this is a whole project. So now we learned, in the last step, we learned how we set up one element, how we set up one model, how we set up the parameters and input data for this one model and do a calculation. But of course, if it gets more complex, you will not do all this in one script. And so that's why we will look how we work with this, these basics we learned now, if it gets a little bit bigger, if we have a whole catchment with different subbasins. And for this, we have included in HydPy an example project. It's the Lahn River, a tributary to the Rhine in Western Germany, in Hessen, federal state of Hessen. And in our example project, we have 1, 2, 3, 4 subbasins. You can download, or you can, you can download the example project from this website, but it's already also included in the repository, in our tutorial repository. So for now, you don't have to download it. This is the network graph we have for our example project. So you can see we have 1, 2, 3, 4 land models. We have 1, 2, 3 stream models. So these are all elements, and between them, between the elements, we have the nodes, because remember, every element can only be connected to a node needs to be connected to an element, and that's how we build our network. If you download the example project, it's a zip file, you have to unzip it, and then you will get a lot of files. This is the project structure. And in this project structure, you will again find the same things we did in the first tutorial for one element. We have, let's start here. We have a network folder. In this network folder, we define our network with nodes and elements. We have a control folder where we define the models. We have a conditions folder with the initial conditions. And of course, we have a series folder with the forcings, with the metrological input data. Let's start with the network folder. In this network folder, we have 3 Python files. And in each Python file, we have, similar to what we just did for one device. So the nodes and elements are, we call devices. So for for 2 devices in the last tutorial, where we defined 1 element and 1 node, here we have some more. And you could put this all in one file, but for the sake of convenience, you can already structure it. And so we have structured it here. We have one file for the elements that are headwaters, we have one file for the elements that are non-headwaters, and we have one file for the elements that are streams. And they all are just defined here. So they have the ID, the name, they have the node, the elements have the outlet node. They also have some keywords. You are free to give any keywords to elements that will help you later structure your project. For example, the nodes also have keywords that you know are at this node there is a discharge gauge, for example. And yeah, and each network file corresponds to one selection. We will later learn what a selection is. Then we have control files. The control files are the files where we define our model, and similar to what we did before, we have here one example control file. So we do a wildcard import for the HLand96 model, and we do the import from the modules where for our submodels and submodels, and then we set all the parameters that are necessary for the models, and here we set the submodels that we need for our application model. So this is similar what we did in the tutorial before. So for each element you have defined in the network group, you need one file, and this file must have the same name as the name you gave to the element. So we have an element which is called land_dil_ASSL. So we need one file, and in this file, the model for this element is defined. Okay, I think I said this. Then we have the series files. There we have the input data. We support currently 3 different time series file formats: ASCII, netcdf, or Python NumPy. And we have the condition file. So again, for each element you define, you need one condition file. And in this condition file, of course, you set the initial conditions for the states that are necessary for the model to run. Okay. And now we switch to the third tutorial, and we will see how we work with such a project. I forgot tutorial 2. This is really short. I will quickly show this, because there's one thing. Maybe you think, okay, there's a lot of code, but I want to see something. I want to see how my catchment looks like. Unfortunately, HydPy does not include data structures for spatial coordinates yet. So we don't store the shape of any subbasins or something like that. Of course, quite often your workflow will be the opposite. You have your maybe you have a GIST project with all your information about the subbasins with the shapes of your catchments, and then you will write a script to produce HydPy projects based on your GIST data. And of course, then you can easily map the network, the HydPy network, to the information about the spatial characteristics of your catchment from your GIST. But nevertheless, there's one little helping tool that will at least give you the possibility to plot the network structure. So this is this code, because we are already it's already quite late, so I will not go in detail here, but with this kind of code, you can save the network structure in a common file format like GraphML or GML, and also use this with other programs, or just plot how your nodes and elements hang together. So this is possible. Okay, but now let's turn to the third tutorial. And in this tutorial, we will learn how to work with an existing project. In this case, the example project LAN. So I will just run the imports. Again, we create an instance of the HydPy class. We call it HydPy HLAN. And if you have a project, like a folder with all the project files we just had a look to, then the HydPy, the instance of the HydPy class you create has to have the same name as your project folder has. And we set the time grids as well. In this case, 5 days and time step of 1 day. And then there's a helper function. So we saw in the last example when we just prepared one element and we had to call methods like prepare series and everything. So if you have everything prepared in a project structure, you can call this method prepare everything, and this takes care of everything. So this makes it easy to leave the HydPy instance in a simulation ready state. And yeah, and actually then we're already ready to simulate. The only thing I do here is I save my initial conditions, because maybe I will change later something and simulate again. And once I have simulated from start to end, the conditions in the conditions here of the project will be set to the new simulated conditions. So that's why I save my conditions. And here it's not necessary to use copy. It will really save it and not be not just a pointer to the same object. So I save it. And yeah, again, I could check which nodes I have. So it's the 4 elements here. And yeah, now we can check if one of the elements has already simulated values. Obviously not before simulating. Then we call the simulate method, and then we see now we got our simulated values for discharge. I said before that I will later give some more information about this mysterious object HydPy.pub, this singleton instance of public properties, which you always have. And this we do now. So with dir, we will reveal all the attributes and methods of pub, but I exclude the private ones here. So, and we see we have, yeah, quite some. We already know time grids. And here we find the network manager I used in the second tutorial. I went quite fast through, but there we used the network manager again. And this network manager is used to, yes, go back again. So here in the second tutorial, we used a network manager. We set a project dir with the network files, and then we loaded the files. And that's how we loaded the network files here to then create this graph. And here we see we have for all the groups of our project, for the conditions, the control, the network, and the sequences, we have a manager attribute, and this manager attribute again holds all the paths. So actually, if you think there is happening some magic, if we call the prepare everything method behind or in the black box, which is, it's not a black box, of course, you can always dig deeper and deeper, and we will see how everything works. So behind the scenes, he will create these managers, and each manager will just read all the files. And if you go into the HydPy pub network manager current path, you will see exactly where the files are written from. And we also have the selections attribute. As I said, in the project structure, we had 3 files for our nodes and elements: headwaters, non-headwaters, and streams. And now you can access these 3 selections. And there's always one selection called complete where everything is inside. So if I only want to access the elements which are headwaters, I can access this selection and I see, okay, there are 2 nodes inside and 2 elements, the 2 headwater elements. If I want to have the streams, I do this, and I have 3 elements with the streams, or I take the complete selection and I have everything. And you can still, you can always create new selections. For example, you could, what we do now is we create a new selection by copying the complete selection. And then we do a sub-selection. First, we could search for all elements upstream of one element. And he will just give us this selection. And search upstream will not change the selection. And then there's another method, select upstream. This will really change the selection. So I copied the complete selection into a new selection object with the name test. And if I select only the upstream elements, then you see, then I have a selection with 2 elements, Land, LAN, map, and stream, LAN, map, Land, LAN, loin. Nice name. And these are obviously in 2 nodes, and these are obviously all the elements which are located upstream of this element here, this element holding a stream model. Yeah, these, you can imagine that using these selections are quite useful. For example, if you want to change some special parameters for your model, but only for headwater catchments, and there are hundreds of use cases where you will work with selections. And yeah, and of course we have the time grids attribute. We know this already because we set it already several times. It's still set now here on a period of 5 days, but because the meteorological forcing data is quite long now with the new release, we have a quite long data sets for our example project LAN. We can change the time grid to a longer period. And then again, we should call the prepare everything method, because we need to reread all the input data and change the size of the series objects and so on. And then we can simulate again. And it's quite fast. And then already we can see here our simulated run-off series. Yeah, so that's all for tutorial 3. So we've learned, if somebody gives you a ready HydPy project, which normally, to remind you, consists of 4 folders: conditions, control, network, and series, with the files, with the network files, with the control files where the model is defined, or models are defined, with the initial conditions for each element, and with the input series. So if you have this project structure and you want to simulate this project, you now know how to do this. You can just take tutorial 3 as a as a draft and as a blueprint, and read the model, select stuff as you need to, set the time grids and simulate, and then access any series from any element as you want. So maybe we can, for example, if you now would like to access some state elements. So this is one element. We go to the sequences attribute, we go to the states sequences. Model is missing. So we need to go to the model, sequences states. And here we see soil moisture for the different zones. So in this example project, we have different zones for our sub-basin, and each zone has a little bit different parameters. So for each zone, we have here the final state of soil moisture. So that's how we can access all this. Yes, and if you still have some minutes, we still have one quick tutorial we want to go through. Go to tutorial 4, and that's and in this tutorial I will show you now how you add a new element to an existing project. Actually, it's already done. I just show you how it looks. So I change to the tutorial 4 is what I want. And in your in the tutorial folder, there is the folder with the example project HydPy HLAN, and then there is another one, HydPy HLAN_dem. And if you go there into the network files, you see I added one more file. I called it dems. So you're really free to choose any name here you want, and this name will later be a selection in your project. And in the dems file, I created one new element, which I called dem. And in this element, into this element, we want to put a reservoir model. So this is the network file I added. I changed, of course, the inlets and outlets in the network structure a little bit. And in the control file section, I added a new control file for the DEM model. And we have, if you later maybe read in the HydPy documentation, we have different DEM application or reservoir application models. One is called dem_lake, which is supposed to simulate a controlled lake. And so I added this control file with all the parameters necessary to set up the dem_lake model, also with some water volume to water level or some relations. So we have one water volume to water level relation, one water level to flood discharge relation, and actually this is here just for the sake of simplicity, just a very simple relation, a linear relation. And so we added this, and of course, I don't need any additional series for this, but of course, I also need an initial condition for the DEM model. So initial condition here is especially the water volume, which I set to some value for the beginning. And then, so this is already all set. You see here in the tutorial 4 that we again create an instance of our HydPy class, but this time we call it HydPy hlan _dem. So he finds the right folder. It's always relative to the current working directory. So you should change if you are not in the working directory where your Python project is located. You should before change to the working directory. And yeah, so we have the dem project here, so you can read everything. And I will just run through it now. And we see, after simulating already, yeah, I simulated already here. And here you can see here the simulated water level, water volume. And what we can see here is, oh, it gets quite high, 300 cubic, I think it's 300,000 cubic meters, something. It's maybe it gets a little bit too high. So maybe it's not very realistic. So we can check our relation, water volume to water level relation, and especially the, just run this, and especially the water level to flood discharge relation. So we see at a water volume of, yeah, even 300 million cubic meters, we have a water level of around 20. So let's maybe say that we do this relation between water level and flood discharge a little bit more realistic. So that's with higher water level, we have much higher flood discharge. So this I actually do here. So I just do a polyline with some more supporting points. And I can plot the new relation. And now we can see, okay, with higher water level, we have a much higher flood discharge. And I saved the initial conditions before. So now I set the conditions back to the initial conditions I saved at the beginning before I started the simulation, that I can start with the same initial conditions again. I simulate, and yes, we see it worked. Now our peaks are much lower. Okay, so this was the last tutorial. And here you learned that with an existing project that you can easily enhance the project. You can add elements just by editing all the files in the project structure. So normally you would first, I go back to the overview of the project structure. So you would first add new nodes and elements in the network folder. You need, for the new elements, you need a new control file where you define the model you want to use for this element. You need the initial conditions for the states that are necessary for the model to run. And maybe the model needs also some additional input time series. Then you would have to put them to the series folder. And then you're all done. And of course, also this is something you would do manually, maybe for teaching purposes. But when you start building a real big project with like thousands of elements, you would, of course, write a script that creates all these files for you. But yeah, you can imagine how this step would work then. And we already have some help, some tools also for helping create projects based on HydPy. So yeah, maybe if the community that uses HydPy gets bigger, we will also see more tools around this core, this HydPy framework, which is like the core of the whole thing, the machine. But yeah, it would be also nice to see some more open source tools that make use of the HydPy modeling framework. Okay, so, oh, sorry, it was a little bit too fast. I wanted to just show the last slide. That's here. So then, yeah, thanks a lot for your patience. It took us a little bit longer, but also because we had some technical issues in between. Thanks a lot. And if you have any questions, use the chance that also the developer of HydPy, Christoph, is here, and also my colleague Simone, and they are both very experienced with HydPy. And yeah, together I think we could answer all of your, or hopefully most of your questions. Thank you very much.